Hi everyone, and welcome to this video on weight, mass, equilibrium and Newton's third law. What we'll look at today, the difference between weight and mass, really often misunderstood or rather confused, why weight changes depending on the location, how to calculate weight using the formula W equals mg, the concept of equilibrium we've looked at in a previous video, but we'll look at again just to reiterate it, and Newton's third law and how to apply it. So the first thing, mass and weight, as I say, it's such a common mistake for people to make simply in terms of getting the units wrong, usually, and that causes a lot of confusion. It's completely understandable because in everyday life, when we're talking about people's weight or something's weight, we very often use the unit kilograms. In fact, what we're talking about if we're using kilograms is the mass. So what is the mass? It's the amount of matter, it's the amount of stuff that something has. There's something called inertial mass also, which we'll look at in another video. But basically the idea of mass is how much matter there is in that object. So it's measured in kilograms, as I said. So talk about something's mass is what you're usually talking about when you're saying, oh, that weighs 3 kilograms, even though we use the word it weighs that much. The mass of an object is the same on the moon as on the Earth, and it is in fact indeed the same everywhere. The mass of something will not change. The amount of stuff, the amount of matter that object has is not going to change wherever it is. Whereas the weight, importantly, is something we're talking about forces here, is the force caused by the gravity on that planet or on that moon, on that large object. Okay, when we're talking about weight, we are talking about a force, and we have to treat it as a force. Of course, it's measured in newtons because it is a force. So the weight of an object depends on the gravitational field strength of a planet. On the moon, it's about 1/6 of the Earth. And as we'll see, on other planets, it varies hugely. As I said before in a previous video, to measure the weight, we use a Newton meter. So how do we calculate the weight? Well, if we know the mass of the object and we know the gravitational field strength, we can calculate its weight. And the formula, which hopefully you're aware of, but should be second nature by the end of this video, is W equals mg. Weight equals mass times the gravitational field strength. As I said, weight is measured in newtons, must be in newtons, we'll look out for the prefixes. Mass is going to be in kilograms, and the gravitational field strength is in newtons per kilogram. Again, those units so important because they tell you what's going on, as we'll see in the next slide. On the Earth's surface, a mass of 1 kilogram has a weight of about 10 newtons. Look out on your exam board. Some boards will accept 10 newtons, but many boards want you to say 9.8. But actually be very, very careful. Look in the question, and it should tell you exactly what value for G they want you to use. But what does that G mean? So the gravitational field strength is a measurement, as the name suggests, of how strong the gravity is in that particular place. And it's equal to the gravitational force exerted per kilogram. So, as I said, on the Earth's surface, G is 9.8 newtons per kilogram. And those units are telling you exactly what it means. It means that if I had 1 kilogram, then the force exerted on that 1 kilogram would be 9.8 newtons. 9.8 newtons per kilogram, or 9.8 newtons for every kilogram. If I had 2 kilograms, then the force exerted would be twice that. So those units are really telling you everything you need to know. Do you need a formula? Well, it's handy, but not essential if you know what these units mean. In most cases, gravitational field strength in newtons per kilogram is numerically equal to the acceleration due to gravity, which is in meters per second squared. So they both have this symbol G, and so sometimes you might see the gravitational field strength quoted as being 9.8 meters per second squared on Earth, or different values for different places. Okay, so don't be put off by those units. We'll see why that's the case in a second. Okay, so an example here. On Earth, Gravitational field strength we're taking as 9.8 newtons per kilogram. So every kilogram there are 9.8 newtons of force exerted on it. There's our formula, W equals mg. What would the weight of someone of mass 75 kilograms be? Well, let's write down what we know again. 75 kilograms is our mass. We know that our value for G is 9.8 newtons per kilogram. So we can use W equals mg, which equals 75 times 9.8, which equals 735 newtons. What would the weight of an iPhone of mass 175 grams be? Well, the reason I put this in, obviously, hopefully you're seeing immediately that this is in grams. So let's write down the weight, which is 175 grams, which we need in kilograms. So it's 0.175 kilograms. Our G, as before, we're still on the Earth, so 9.8 newtons per kilogram. Use the same formula. And what do we get? W equals 0.175 times 9.8, which equals 1.7 newtons. This time we've got a ball of weight 2.5 and we want the mass, but the same idea applies. I'm going to write down the information and substitute, don't forget. So this time our weight is 2.5 newtons. Our G is still 9.8 newtons per kilogram. We can substitute into W equals mg, which is 2.5 equals m times 9.8. And then our m equals 2.5 divided by 9.8, which equals 0.255 kilograms. So an additional question here, just to prove a point here. If that 0.255 kilograms is dropped, what is the acceleration? Well, the point I want to make here is we could use the formula we've used in the previous video. We could start looking at F equals ma, which is very similar to the formula W equals mg, but we're using directly Newton's second law here. Let's see what we know. Well, we know that this object's weight is 2.5 newtons, and of course weight is a force. It's the only force on it, no other forces, so that is our resultant force. So we can say our F is 2.5 newtons. We've worked out what our mass is. We know that mass is 0.255 kilograms, and so we can work out what A is. A, let's substitute in first, 2.5 equals 0.255 times A. A is 2.5 divided by 0.255, which equals 9.8. This is an acceleration, so it's in meters per second squared. But as I said in the previous slide, this is our 9.8. That's the acceleration. It's exactly numerically the same as our gravitational field strength. And so we can apply these rules and we can say that G can be either 9.8 newtons per kilogram or 9.8 meters per second squared. It doesn't matter what mass you use or what force you use, you're going to get this value of 9.8 meters per second squared. So one final example here on Venus, just to work out the actual gravitational field strength on Venus. If we had an example here, on Venus, I still have a mass of 75 kilograms because that's my mass. It's not going to change. That's going to be the same everywhere. But my weight, due to the gravitational field strength of Venus, is only 675 newtons. What is the gravitational field strength of Venus? Well, it's back to being a fairly straightforward one. We can substitute the information in and find out what our G value is. So we know that M is 75 kilograms. We know that our weight is 675 newtons. We want to know our G, so we're just going to substitute in again. 675 newtons is our weight, equals 75 is our mass, times G. So G is 675 divided by 75, which equals 9.0 newtons per kilogram. And if you put 9.0 meters per second squared, that would be fine as well. As I say, they're interchangeable, but for this particular question, it makes more sense. We're literally talking about how many newtons per kilogram, and that is what our value for G is telling us. Okay, over to you for some practice questions. Let me move this, pause the video, and have a go at those. So hopefully you took into account the prefixes, which there are quite a few random prefixed values there, and here are your answers. Okay, so back to the idea of equilibrium. We looked at this briefly in the previous video. I just want to reiterate some points about it. So the definition of equilibrium is when all forces acting on an object are balanced, and therefore the resultant force is zero. And what does that mean if the resultant force is zero? Hopefully from the previous video you know that two things can happen. It could be a static equilibrium. If an object is stationary and it's in equilibrium, then the object will remain stationary. But if it's in dynamic equilibrium, in other words, if it's moving and it's in equilibrium, then it continues to move at a constant velocity. I'm stating that again. I said it in the previous video, but it's so important. This, particularly the second one, dynamic equilibrium, the idea that an object is moving, it will continue to move at a constant velocity, even when there are forces acting on it. But if all the forces add up to a resultant force of zero, it is in equilibrium and it will continue to move at that constant velocity. So here's the two examples. A book on a table. We've got our weight downwards. We've got our contact force or our normal reaction force upwards. They are opposite and equal. Therefore, that book will stay in a constant velocity of zero. It will stay stationary. This car, here's the confusion potentially. This car has a force forwards, it has a force backwards as well. If those forces are equal, then that car will continue to move at a constant velocity. So it's still moving. The resultant force is zero, that car is in equilibrium. It's not the same. Okay, I've talked about these forces being balanced. I've talked about them being the same value. I've talked about them being in opposite direction, but they are not, and we'll come to this in a couple of slides, they are not an example of Newton's third law. Okay, this is a very common misunderstanding about Newton's third law, which we'll talk about. But these particular forces making an object in equilibrium, they are not an example of Newton's third law, where people talk about opposite and equal action and reaction. I'd looked at this slide before in the previous video, but there's no harm in having a go at it again, making sure that you're completely happy with it. So have a go at filling in those gaps. Pause the video, I'll come back to the answers. And the answers, if the resultant force is zero, the object's velocity stays the same even if it is stationary. Okay, it can keep going at a constant velocity or it will remain stationary. If the resultant force is in the direction of that movement, it's going to cause it to accelerate. If it's in the opposite direction to which the object is moving, it's going to decelerate. So Newton's third law, what does it mean? If it doesn't mean that those forces of equilibrium are the Newton's third law. They're equal and opposite. So why are they not the third law? Here's what Newton said. Whenever two objects interact, the forces they exert on each other are equal in magnitude and opposite in direction. Well, that sounds very much like what we said before with our book, the previous slide. We had the downward force of the weight, we had an upward force, normal reaction force. They were equal and they were opposite, but I said they were not Newton's third law. So here's some additional information you need. For these pairs to be Newton's third law, they need to be the same type of force. They need to be opposite in direction, they need to be equal in magnitude, and they need to act on different objects. So if you think about that book, they were opposite in direction, they were equal in magnitude, but were they the same type of force? Well, the book had a force downwards, that was its weight, that was a force of gravity pulling down on the book. But the upward force was not a gravitational force. The upward force was a normal reaction force. So already we know that could not be Newton's third law. They also act on different objects, which is not the case. Those were both acting on the book. The weight and the normal reaction force were acting on the book. So that does not constitute Newton's third law. So here's the part of the confusion. You will see this in every many textbooks. Every action has an equal and opposite reaction. It's stated in so much documentation, and it's stated by many teachers as well. I mean, there's some truth in it, but I just don't like this definition because it causes this confusion. It needs more detail. As we said, we talked about that book. Here's a man here. The chair is pushing up with a reaction force. The weight is pulling downwards. They are different types of force, so they cannot be Newton's third law, even though they are equal and opposite, equal in magnitude and opposite in direction. The diagram does not represent a Newton's third law. In fact, the force pair is the Earth pulling down on the man with a gravitational force, and the man is pulling up on the Earth with a gravitational force pulling upwards. Quite tricky, this, but the man has a mass. Because he has a mass, he is also exerting a gravitational pull, a gravitational force. So the Earth has a gravitational force pulling down on the man, and the man has a gravitational force pulling up on the Earth. They are equal in magnitude and opposite in direction, and that is what Newton's third law says. So you can use this template. All I'm doing here, we'll look at some examples in a second, but all we're doing here is applying the bits that I'm circling here. You're going to fill in the gaps for whatever the object is. So object A, the name of the force, object B, the size of the force and the direction. And then for the second part, you swap object A for object B, swap object B for object A. The force is going to be the same type of force, the size is going to be the same size, and the direction is going to be opposite. So let's see how that applies to an example where we've got a jet ski here. What does Newton tell us about this? Well, how does a jet ski work? What it does, the jet ski is forcing out water. It's putting a force on that water. A thrust force is pushing that water backwards. As a result, the water will also produce a thrust force on the jet ski. And that force is going to be in the opposite direction, to the right. They are going to be the same magnitude. So how can I apply this template to that example? I can say when a jet ski applies a backward thrust force on the water of size, for example, 2000 newtons backwards, then the water also applies a forward thrust force on the jet ski of the same force, 2000 newtons, and in the direction forwards, the opposite direction. What about this one? A football being kicked by a boot or by someone. In this case, let's see how this works. The ball applies a contact force on the boot to the left. You can see the boot is having a force applied on it by the ball here, and the boot is also applying a forwards force on the ball. So when the ball applies a contact force on the boot of size 20 newtons to the left, the boot applies a contact force on the ball of the size 20 newtons to the right. Same size, same type of force, but one is the boot on the ball and the other is the ball on the boot. One is to the left and one is to the right. Can cause a lot of confusion, that. So have a look at those examples, rewind if you need, check what you're doing, and then have a go at these examples. So describe using Newton's third law why a car moves forwards. Have a think about that, write down what you've got, and come back in a couple of seconds. So the answer is, when a car's tyres apply a frictional force on the road of a particular size backwards, the road applies a frictional force on the car's tyres of the same size and forwards. So the car's tyres apply a frictional force on the road, and the road applies a frictional force on the car's tyres. They're the same size and they're in the opposite direction. So what does that mean? Well, it means that the car is going to be having a force exerted on it forwards. It's got a mass, and that force is going to be probably large enough to make that car accelerate forwards. So surely, if the car is pushing back on the road is going to accelerate backwards. And that sounds strange, but it is actually true. It's just that the road and the earth that it belongs to is way, way, way more massive, and it has a much, much larger mass than the car. So the car, that force will accelerate the car forwards. The earth is going to accelerate backwards very, 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 very slightly, imperceptibly, and so we don't acknowledge it at all. Okay, but it is pushing back on the earth. It is accelerating the earth a tiny, tiny amount, but just so small that we can't notice it. Have a go at another one. Describe using Newton's third law how a rocket takes off with a force of 20,000 newtons. Pause the video, have a go using that same template. And so the answer, when a rocket applies a thrust force on the exhaust gases of 20,000 newtons downwards, the exhaust gases also apply a thrust force on the rocket of 20,000 newtons upwards. So in this example, we would have a rocket exerting a thrust force downwards 20,000 newtons. The rocket is exerting that force on the gases, but in return the gases are also exerting a force of 20,000 newtons upwards on the rocket. These gases will accelerate very, very quickly downwards, and you'll see those bellowing out from the bottom of the rocket, but the rocket in turn will accelerate upwards. Of course, the size in both of these questions, the size of that acceleration is going to be related to Newton's second law. We'll know what the resultant force on each object is, we'd know what the mass of each object is, and so we could work out the acceleration. Okay, I hope you found that useful. You should now be able to differentiate between weight and mass and calculate weight using W equals mg. Explain the conditions for equilibrium, whether something is stationary or it's moving, what that means is going to happen if the object is in equilibrium, if those forces are balanced. You should be able to apply Newton's third law to describe action and reaction force pairs and use all of these ideas in real-world examples. Okay, hope that was helpful and look forward to seeing you on the next video. So if you found the video useful, don't forget to check out other videos on this platform or go to my Facebook page here where I've got other free resources, or feel free to book a call at tobytutorsphysics.com as well. See you soon. Bye.